Okay, so if you still have the same experience, then we will know that it's not on my side, but hopefully things improve. So let's continue. Anyway, access time. Access time um, really speaks to the speed of the memory. Obviously, some memories are slower than others, but access time means how speedy or how quickly the memory can respond. So for instance, imagine you give it, it's usually made in terms of the read operation. So usually access time is more in terms of the read operation. And when we are reading, we supply the address, okay? And then there is a time lag after which information appears. This information appears at the output of the memory so that the CPU can pick it up. And so the time between when you supply the address and when the information appears at the output of the memory is what we call the access time, and it can be denoted as T access. And so if you see T access, that is access time of the memory. If T access is short, then the memory device is fast, obviously. CMOS devices tend to be faster than bipolar and NMOS, but in general, these we are talking about nanoseconds, somewhere between 10 to 20 to 50, some even up to 500 nanoseconds, but still very fast. Now, when we look at main memory, these are values for main memory, which we said is the main memory where the semiconductor memory where you keep the instructions. Actually, the main memory is also called working memory. When we are looking at auxiliary memory, as we said earlier, it is slow and it can be much slower than 500 nanoseconds. Volatile memory is a type of memory where you need electric power for the memory to continue keeping that information that you kept there. So you need you need electrical power to be on for the information to be stored. If the electric power goes off, the information will also be lost. And so this is as opposed to non-volatile memory. Non-volatile memory, which continues to store information even when power has gone off. So for instance, your computer, your auxiliary memory, your main memory, all those memories are non-volatile. That's why you can switch off your computer and tomorrow you switch it back on and it starts. The memory in your phone, the memory in all of these places or all of these gadgets is non-volatile. But we also have volatile memory, which needs power to stay. So for instance, you know how RAM works, random access RAM. So for instance, when you are working on your computer and you've not saved things, those documents exist in the computer because they are kept in a certain part of memory. But unless you save them, usually when you save information, you're saving it on auxiliary memory. But if you don't save your Word document, and then power goes off or you switch off your computer, you're going to lose those documents. It is because they were stored in a certain part of volatile memory like RAM, and then all of a sudden you lost power and the information got lost. So that's the difference between volatile and non-volatile memory. Obviously, most memory is non-volatile. Random access memory. Random access memory or RAM. This is a type of memory where the time to access any part of the memory is the same. Okay, so if we go back to here, we can see how we have arranged our memory and so on and so forth. So whether I want to access register 0 or I want to access register 7 or I want to access register 16, these will take the same time. That's what means by random access. Whichever you're accessing any part of the memory, it will take the same time to access that memory. And I think you know that most memories, so for instance, most of the memories that you know will be random access. If you are on a CD, if you're playing your audio on CD and you have your songs there like MP3 songs, and then you are playing song 2, but then all of a sudden you want to play song 7, you probably have a remote or you press a button and it will go to song 7 immediately. Whether it was song 16 or song 32 or song 12, the same time lag will happen until you start playing that new song. That is random access memory, where the information is stored within the large memory device. Does not matter, the time to access it will be the same. This is as opposed to sequential access memory. Sequential access memory, or SAM, where the time of access of that memory depends on its position within the memory device, so within the larger memory substrate. So for instance, you might find that you have your address is 000 all the way to 111. And so when you want to access memory like SAM, it will start at memory 000 and it will go through all the memories sequentially until it reaches the 1111, which is the position that you wanted to access. That means that if you wanted to access 001, it will have taken a shorter time because in this sequence, it will reach that memory position first. If you wanted 101, it will reach it first before that 1111. So the farther your memory register is somewhere hidden inside there, the longer it is going to take to access. And that is called sequential access memory. I actually don't know if you remember the tapes that we use, the tapes that we used to play in radio cassettes, where you have your songs, like 10 songs, for instance, on side A. It was quite funny actually. And you want to play, you're playing song 1, you want to play song 20 or song 5, and then you have to find it. Those cassette players used to have a forward and a backward, so you can forward at speed or back behind at speed, or we would use big pens and put in there and just try to find the memory. But you cannot even be sure that you've reached the song. You have to put back, play a bit, and see how further away you are, and that is sequential access memory. Because you cannot just jump in memory and go to wherever you want. Okay. I think Maureen remembers. Some of you may not remember, but actually some of the older cars, including mine, they still have that radio cassette. It's just that we no longer have those magnetic tapes. But yeah, that was the technology. That was the technology at that time, together with what you might call, if you remember floppy diskettes or floppy disks. A floppy had 1.44. Sorry if I went off there briefly. A floppy had a floppy disk. I don't know where they went, floppy disk. This had 1.44 megabits of data. That was the capacity. That was your flash of that time. and so you could put your document and you go to a computer and print it and so on. So yeah, non-stop audio songs like these mixes that I see these people doing these days of 1 hour, 2 hours. Yeah, you could say so. Yeah, you could say so, or videos, you could say so, because I mean, that song is not going to be kept in one register. It's going to be broken down into many registers. And so for you to jump to minute 47, you need to find a way to jump there. It is not a matter of you press a button and you jump there in an instant. Yeah, so I agree. Okay, let us look at read-write memory. A read-write memory is a memory where the reading operation and the writing operation can be performed with equal ease. Okay, so we can both read and write with the same amount of, I don't want to call it difficulty. It is equally as easy to read as to write. And so these are memories where we can read and write. And your flash drive is an example of a read-write memory. Because you can copy things onto your flash, you can copy things off of your flash and put them in the computer, etc, etc. Another example of memory is read-only memory. Read-only memory is so-called ROMs, are memory devices where the reading operation happens way more often than the writing operation. In fact, with some types of ROMs, we can only read. It means we can only access the information on that. We can never write into it. And in fact, that really is the meaning of read-only memory. So some of these types are of course, you are reading something that was written there. So at some point, somebody would have had to write something there. But usually this is done at the manufacturing stage. So, the manufacturer actually writes information into that memory, and once it leaves the factory floor, the only operations that can happen on those memories are read. You can only read, you can never write. Now, read-only memories are used in places or programs which do not have to change. So for instance, do you know the cashier's thing? The cashier in the supermarket, that thing that reads, records, and calculates the money and what? Just scan, like a scanner really. It always scans every day of its life. All it does is scan. And so that the program within that never needs to change. You never need to write. Usually when you are writing, it means you are creating some improvements or something. And so something like that can have, or usually uses, read-only memory. Your refrigerator at home, the microwave at home, it does the same thing every day. And so for it, it just needs to be able to read only when they are manufacturing it, or the barcode reader, yes. When they are manufacturing it, they write the program inside there so that it is able to perform in a certain way. And after that, all it does is just read. Now we have read most memories. These are the memories where most of the time we are reading, but we can also write some of the time. Just usually, rarely do we write. But these are ROMs that allow us to write. So it means we can change the program if we want. We can update the program, etc, etc. A CD is also a read-only memory. Although there are some read-write CDs, by the way, or there are some where you can rewritable CDs. I remember they used to be there and they were a bit expensive, and before they knew it, flash drives came and and then they were no longer useful to anybody. I don't know who still uses flash, who still uses CDs. But yes, the earlier types of CDs were called read-only CDs actually, or CD-ROMs, so-called compact disc read-only memory. Okay, CD-ROM. But there were also rewritable memory CDs, so you should read about those. Yeah. Then you have static memory devices. Yeah. So with static memory devices, just a moment. Yeah, with static memory devices, if you store information in a static memory device, that information will be stored there permanently as long as the data is applied. So you have these memories where as long as there is power, you will store that information and it will always remain there. That is static memory. So it sounds like volatile, but actually they are not quite the same. I'm just going to give you a clearer comparison when we deal with dynamic. With the dynamic memory, yes, you also need power for the information to be stored there, but just because there is power does not mean that that information will stay there. It can actually disappear. And so with the dynamic memory devices, the only way to ensure that that information stays there is we have got to refresh it. So every time after like 1 millisecond, we refresh the information so that we can start afresh after another millisecond, we refresh the information. Here, the information is permanent as long as there is power. So both of these need power, but with static, the information will stay. But with dynamic, the information will usually disappear unless you keep refreshing it, even with power there. Now that means static memory is like a flip-flop, because if you have a state in a flip-flop, it will not change as long as there is power. But with dynamic, you're looking at something like a capacitor. So the memories that are based on capacitors usually require refreshing. The reason is because capacitors drain. I think you know that the power on a capacitor drains. So for instance, if you say that the charged capacitor is bit 1, and when it is not charged, it's bit 0, and yet it drains over time, it means that bit 1 can eventually turn into bit 0 because the capacitor will eventually drain towards 0. However, after some time, you can just refresh so that whatever was 1 goes back to 1, whatever was 0 will of course stay 0. So we are going to look at an example of this later on in the course, in these lectures, maybe in a couple of lectures to come, to see how this refreshing is done in such a way that a 0 stays a 0 and a 1 stays a 1. With volatile, it is after you remove power that the information will be lost. And so you could say both static and dynamic are also volatile. Okay, so under volatile, you can put static and dynamic, but then you say that this one needs refreshing, whereas that one does not need refreshing. Okay, so that is that. Main memory is also called working memory, and it is semiconductor based, and it is that place where you store instructions usually. So when you switch on your computer knows what happens next, how it is supposed to boot, and so on. And so that information usually, at least for the booting, is kept in a bootstrap memory. And actually that bootstrap memory is usually not even main memory. It's usually flash memory. We are going to look at it later. Flash memory is even faster. And so after that, the other instructions, the booting is the one that says, do this, do this, do that. But the rest of the information that helps your computer to boot up, for instance, is within the working memory or the main memory, which is a read-only memory. Then you have the auxiliary memory, which is like your hard disk. So when you are saying my computer has 1 terabytes, actually that is not main memory, that is auxiliary memory. Usually the main memory is small, usually contains most of the instructions required to run the computer, but is not going to store data. You're not going to store your videos and your movies and photos on main memory. Now, I should mention that even if you are working on a document that is stored in auxiliary memory, when main memory is working on it, it will usually pick it out and work with it within the main memory. And after it has finished its operations, it will send it back into auxiliary memory, or it will update the auxiliary copy. And so when you are working, usually the information, the instructions that are being executed, together with the work on which that execution is happening, are usually kept in main memory. But when you finally save documents, they don't go in main memory. So these are the main terminologies, and you can see we have spent a whole hour discussing them. They are really almost an hour to be specific. They are really important. They are really many. We are going to meet probably some others, but so far I think this gives us a big roundup of most of the ones that we are going to meet as we go through this chapter. Not really. Main memory is ROM. Main memory is read-only. RAM is random access. In fact, if you store information in RAM, when you switch off the computer, that information is lost. I think you know that you cannot store things in RAM. What we call RAM, I know, what we call RAM. My RAM is 4 GB and so on and so forth. Really the speed with which we can work. But ROM is where you store instructions. So you are booting information, or the files that you require for booting cannot be stored in RAM because then they will be lost. Okay, I think I may have gone off, but I should be back now. Somebody keeps calling me, I don't know why. Even when I switch them off, they keep calling me. So let us look at an example. We have a semiconductor memory chip specified as 2K by 8. How many words can be stored on this chip? Obviously, there are 2K, which is 2 times 1024, which is 2048 words. Okay, we've already looked at this. The word size is 8. Okay, so the word size is that part. And how many total bits can this chip store? It is 2048 times 8. I don't know what that is. We have a memory that stores this. Okay, which memory stores the most bits? 5M times 8 or 1M times 16. I don't know. This is about 1M times 16 is about 16M, and 5M times 8 is about 40M. So if you do the math, really, you can see that this memory stores more. So we can say that the 5, okay, we may not say that. If these memories were on the same size of substrate, we could say that the 5M by 8 is the denser memory. It has a higher density compared to the 1M by 16 memory. Now let us look at this example. So the general memory operation is something that we have already looked at. You must provide the address. That address is used to identify the specific place in memory where you want to perform your operation. Then you give the command to either read or write. When we read, it is different from when we write. When we read, we select, okay, so let's say we've already done our addressing and we already know the memory word that or register that we want. When we read, information in memory appears at the output, okay, at the output of the memory. So it appears at the output of the memory, and that information, the CPU can then pick it off of the output of the memory. Now, when we write, we must provide information to write. And obviously, when we write, nothing appears on the output. So this information to write at the input, we provide information at the input, and that information will be input into the, or written into, or stored into the memory. So you can see these are two different functions, and what is happening at the input and the output is totally different. Now, sometimes this is the last point. We need to do some control. This control, we have to control the memory. I think you know that within the computer there are some control signaling. We can enable the memory, or we can disable the memory. If we say memory enable, we can say memory enable, we can say chip select, we can say chip enable. There are so many different ways you can deal with this. But yes, we can either enable the memory or disable the memory. If we enable the memory, it means then we can either write into it or read from it. If we disable it, then we cannot do either of those. Let us look at this 32 by 4 memory. You can see it is 32 by 4. 32 is the number of words. So 32 is equal to 2 to the power 5. And that means we need 5 address bits. And these are going to be from 0000 all the way to 11111. So that each of these words which are in a register Each one has its own 4-bit register because the size of the register is 4. Each of these can be uniquely identifiable. Now, the number of inputs is going to be equal to, the number of input line is going to be the number of the word size or word length. Because these are 4, we need 4 lines as data inputs. Even the outputs will be the same, because if we are writing information in here, we provide our inputs in through that. If we are reading, our information will come out through those outputs. Now, if we have 4, our word length is 4 bits. We don't need 8 input lines. 4 input lines clearly are going to be enough. Now, these are my address bits. You can see there are 5 bits from A0 to A4, 32 by 4 memory, read write. Now, the read write commands are given as read write, meaning that if we put a 0, this is active high, and the write is active low. If we give a 0, it means we want to write. So if you want to write, make that a 0. If it is a 1, it means you want to read. That means that if I put a 1 here, usually you start with the address. This is your first step. And so it will select, maybe I've given it 00000. So it will select my, whatever the register there, the first register. And then my read write command is a 1. That means I want to read from that. It means that the information here, what the memory does is that it moves the information here to the output. But if I had given a write command, which is a 0, it wouldn't bother with the outputs. It will usually look at what is on the input so that it can write it into that memory. Now, the memory enable also needs to be selected. And so usually this is step 2, and this is usually step 3. So after you give the command to either read or write, you deal with the memory enable. So you can make memory enable 1. Because if it is 0, then it is disabled. You can see that ME is active high. Okay, now how do we ensure that usually, okay, so usually these are tri-state inputs and tri-state outputs. So if we are writing, that means information appears at the inputs. Usually the outputs in that moment will be in the high Z state. I think you remember the high Z state. In other words, they'll be disabled. There's nothing that can appear there that can get to the output. Remember, usually this information, you have buses here, okay, data buses that usually take that information to the CPU. You also have data buses here that bring information from the CPU. We are going to look at that in a short moment. And so you can see that usually you have your cells, and each cell has a unique address. And so if I want to write into this, I can give this address, and I give information that I want to write in there, maybe 1011, and then I give the memory enable, and then this information will be transferred into this register. Okay, that is how we write or we read. Yeah, same thing, same explanation that I've already given. And even this is same explanation, really. So this is right. Describe the conditions at each input and output when the contents of address location are to be read. Okay, so this is a read command. You give the address, which has been given as that. Data input, when we are reading, we don't need inputs, we only need outputs. So data inputs are XXXX not used. You can even say they are in the high Z state. Because we are reading, our read write should be high. And then we give memory enable, which is active high, and then we can read our information from that memory 00100. Let's see, 00100, this information. Yeah, you can see, I don't know, is it 0001? Or maybe this is not the same example that, yeah, 00. 01 is the information here that will be read. But if we were writing, first of all, you can see that the question is different. Describe conditions at each input and output when the data word 1110 is to be written into address 01101. So once again, we give the address, but in this case, we put the word that we are writing on the input lines because you need to write it. So you need to provide the word. And then we want to write, so we give an active row write command. We enable the memory, and this information will be written into that address, which is 010. I don't know. It really works out. I don't know which of these addresses it is, but it really works out the way we expect. Now the data outputs will be in high Z. Should be in high Z, not all the time, but yes, memory devices that make sense would require that is in the high Z state, so that there is no information that is appearing at those. Now, I should also mention here, actually, before we leave this, when I was talking about these lines and those lines, data lines, or the data bus. A bus is a combination of lines, of course, that we could use the same data bus to provide information for writing as to provide information for writing as to retrieve information or fetch information that we are reading. The reason why we are able to do that is because we cannot read and write at the same time. We cannot both read and write simultaneously. So that means when we are reading, and so we can use the data lines. And when we are writing, we are not reading, and so we can use still the same data lines. Obviously, that is why we put, if we are using the inputs, we put outputs in high Z so that there is no collision on the line, on the bus. Okay. But the example, Kalulu, the example is quite clear because it is essentially what I've been talking about the whole time. That it is really based on the procedure. Number one, provide address bits or address information. This information will identify which part of memory, which specific register you want to deal with. Two, if reading, make read write high, okay, because you want to read. And three, enable chip. So that means maybe memory enable is equal to 1 or chip select is 1, whatever. And then 4, your information appears at the output, data output. So that's where you read data outputs. You can read your information off of the data outputs. This is for this case. This case, we are writing, but their procedure is essentially the same. Once again, you provide addresses. 2, now because you are writing, you need to provide the information that you are going to write. Provide info at the inputs. 3, make read write equals 0 so that you are able to write. And then 4, enable chip. So once you enable chip, once you enable the chip with your memory enable as high, the memory will already have resolved the address. It will know which register, and it will also know which command, whether to read or to write. Okay, now read write is also sometimes written as just write with a bar. It really means the same. That if it says this one is a 0, write. If it's a 1, read. You can also write it, you can also write it as write enable. Okay, if it is 0, write. If it is 1, read. When writing, isn't the data at the inputs moved to the outputs of the memory? Arvin, no. I said that, is there a way the outputs are kind of disabled during writing? This is precisely what I said, that the data outputs when we are writing are in high Z. What does high Z mean? I think I explained what high Z mean. What high Z really means that let me just open a new slide and try to explain that a little bit for those who don't remember. High Z, and so you have, this is your memory, for instance. And then you usually have what we call output buffers. Okay, by the way, these output buffers also have usually sometimes a chip select. And this is, let's say they are 4 bits. You have, so this is your memory. So even if this memory appears at the outputs, at the inputs of the buffer, this is called an output buffer. And these are your outputs. This one can, if this one is high, it is set to 1, that information will never cross over from here to there, because you see this thing is disabled. Okay, so you can use those output buffers to do that. But you've also seen, we talked about the tri-state. When we have high Z, where we have an icon like that, when we have high Z, what happens is that usually there is a high resistance that comes, along those lines. And so the information is not able to jump over those resistors to appear at the output. But when you remove the high Z state, those resistances go away and your information is able to flow. Remember, this is current. It's really a voltage and a current. Hopefully that answers your question, Arvin. Yes. Right, okay. Let's see if there are any other. Okay, thank you. So we have some simple question. Here we have a 4K by 8 memory. How many data input lines and data output lines? Obviously, the data input lines and data output lines are equivalent to the size of the word. And so those will be 8. Each of them will be 8. How many address lines does it have? We need 1 address per word or per register. And so 4K is 4 times 1024, which is 4096, which is actually, in terms of powers of 2, it is 2 to the power 12. So it means we will need 12 address bits, because if we have 0000, 12 times to 1111 12 times, we are going to have 4096 unique addresses, and each of these can be allocated to each of the 4096 words. And the capacity in bits, you know that. So the memory connections are important. So we have a CPU here and we have our memory on that side. We need to have a bus that takes addresses, and that is the address bus. Only the CPU sends address information to the memory. If the CPU wants information from a certain register, it has got to supply the address of the register. The memory is not the one charged with knowing what the CPU wants. The CPU must supply that address. And so we need an address line or an address bus where that information goes, but it only goes in one direction, from the CPU to the memory. The memory never has to send address information back to the CPU. And so it is a unidirectional bus that takes the address. The address bus is a unidirectional bus. Now this bus obviously has several lines. So if it is like a 4-bit word, then you're going to have 4 lines, or 8 lines if it's 8-bit word, and so on and so forth. That's why there are these dashed, these little whatevers, to show you that they are actually a combination of signal lines. Now, the data bus, the CPU sends information to memory to write, or it receives information from memory when it is reading. And these, as we said, do not happen simultaneously, and so we can use the same data bus to send information there or to receive information from there. That means the data bus is bidirectional. It moves in both directions, but not simultaneously. Then finally, we have to be sending information from the CPU, control information from the CPU to the memory, and so we need another control bus, and usually this control bus, once again, is unidirectional. And some of the control signals obviously are the read-write, it is the memory enable, and so on, and we will probably find other types of control signals. By the way, sometimes the enable inputs are 2. Sometimes you find that you have 2 enable inputs, like chip select and chip enable, for instance, and both of these need to be in their active state for the memory to be enabled. And then one of them, usually if the memory is not working, it can be put in a certain state where the memory can go into a low power mode so that it can reduce on the power it's consuming. But we are going to see these types of memories where sometimes you have to enable inputs. Okay, so that's it. That's it about CPU memory connections. You just need to remember that we have 3 types of buses: the address bus, the data bus, and the control bus. And the data bus is bidirectional, whereas the other 2 are unidirectional. Actually, you can even see here that this is your input and that is your output. And so if we are inputting, meaning we are writing, we can also be we can't also be outputting, because then you're going to have a clash, you're going to have interference between those signals. Okay, let us look at read-only memory. This is read-only memory obviously has addresses. There's a bigger table that this is based on hex, but you can see it has 8 data outputs that have been converted into hexadecimal. Okay, and the addresses have also been converted into hexadecimal, but they are 4-bit addresses. I think you remember hexadecimal, but there is a part of a table here that I didn't include. So if you're worried about hexadecimals, you'll still be able to find a normal binary table. So this is a 4. No, this, because you have 4 addresses, it means the words are 2 to the power 4, which is 16. And so this is a 16 by 8 memory, and it is ROM, and this says that it has tri-state outputs. That means that when this chip select is disabled, these outputs are in high Z. high Z state. This is chip select, which is the control input, and it is active low. So if you want to read from this memory, you have got to make that low. Now there is no read write control input. The reason is we never really write into ROM. We only read from ROM. Now for the read mostly memories that we talked about, which are also ROM, but it's just that we read a lot more times than we write. It's just that in their, by their very nature of the information stored there, we never really want to change it a lot. It's like updating your phone. Okay, yeah, it's like you're just updating firmware from time to time. So that can be like read mostly memory. Most of the time you are reading, but a few times, once in a year, you want to write. And so, but here strictly ROM read only, where this is done in the factory. This read write, we don't need that command because we are always reading. So all we need is to provide the address and then enable the chip, and the information from that address will be provided at the output. Let us look at a model, an interesting model for a ROM, a read-only memory. Usually read-only memories are, or memories in general, usually are arranged in some kind of array. We call it a register array. So I could say that I could draw this mesh, and then I can say that at each of these locations, I have a register, okay? So this would create like a square array. I have a register, and the number of words here are 16, and obviously the number of the size of the word, or the word length, can be whatever I want it to be, depending on the size of the registers. So this is, you can see this arrangement is like 4 by 4, similar to what I've just drawn, but at each of these there is a register. And this register is drawn as a box, and you have an enable and an enable, okay? So it means that for you to enable this register, you need to supply a high here and a high here simultaneously. If you do not do that, that register will not be enabled. Now, how do we supply? So if this is 16 by 16, it means we have 4 address inputs, okay, which is maybe A3, A2, A1, A0. So you can see that these have been arranged in 2 columns. So you have column 0, 1, 2, 3, and rows, which is row 0, 1, 2, and 3. And so if I supply my address, it means that I can select 1 row and 1 column, like here. So for me to identify which address I need, I can come, let's say for instance, I want that address. I can come and select row 1, and I select column 2, and it means that my address is putting me there. This is the register that I have selected. That's essentially how this works. Now for the row select, or for you to select the row, you use a decoder, okay? A decoder is 1 of 4. A 1 of 4 decoder, and for the columns, because there are 4 columns, you also use a 1 of 4 decoder. You remember that with a decoder, you have an input and you select 1 output. That's how a decoder works. So let us look at an example like, let's say that we have A3, A2, A1, A0. These higher significant bits will usually be used for column select. So you use the higher significant bits to select the column, and these are for row select. So if I have my A0, A1, it will be 0, 0, 0, 1, 1, 0, 1, 1. It means row 0, row 1, and so on and so forth. So depending on what I have there, I select a certain row. Same here, A2, A3 can be 0001, 1011, and so that can be column 0 all the way to column 3. So depending on what address I have, I can select either a row and a column. Now let's say that my address is 0000. If it is 0000, I will select row 0. That is row 0. Let me remove that. And I use this. I will select row 0. Okay. And I will select column 0. I don't know how to draw this. Let me just draw it. I will select column 0. But you see, when the line, by selecting row 0, it means row 0 will be high. The other rows will be low. That's how a decoder works. It will make this high and the others low. And column 0 will make those high and that one low. So if we look at row 0, if you follow row 0 here, you have that. If you have a high going here, it means this side of the register is enabled. In fact, even for these ones, that will be enabled, that enabled, that enabled. But for column 0, we look for column 0. It is this line. This is enabled, 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 and enabled as well here. So we can see that the register 0 is the only register that is enabled both sides. These are enabled, but on the other side they are not. These are enabled, but on the other side they are not. So that means my address 00 has enabled both sides of this register. And so this is how I'm resolving that this address gives me that register. It does not give me any other register. Now, I'm reading, obviously. So if let me remove that one. Okay, so we can see that because I activated row 0, it is high, and column 0 is also high. We can see that this high comes here, and for column 0, that high also comes here. Although, of course, the high also comes here and there, but on this side, there are zeros, so those registers are not enabled. Now, we see that if we are reading, the information comes to that bus. This is a data bus. And we are reading, so the information on that in this register goes on the data bus, but there is no other register that has information on that data bus because all of them are not selected except register 0, and that information will flow along the bus and come down here. You can see this number 8, it is telling you that the size of the word is 8, and so in there, this is an 8-bit data bus. It comes into the output buffers. Output buffers, you can see, have a chip select. And so if that chip select is 1, sorry, the output buffers will be in high Z state. And so you could say you have high resistance here. Really high Z means that it's like a blockage. So you have high resistance, meaning the word cannot, nothing can go through, the signal cannot go through. And so chip select is 0. It will enable this so that your information can appear at that output. But if it is 1, then the information will reach here, but it will not cross the buffers. Okay, is that clear? If you have any questions, now is a good time. But if you don't have any questions, let me ask you. Which register will I actually resolve if my address is 1101? What register am I looking at if my address is 1101? Okay, let me see. Okay. Okay, so we know that column select will be A3, A2, which is 1, 1. So we select column 3. Then row select is A1, A0, which is 0, 1. So we select row 1. Remember, our rows start from 0. So if I'm looking at column 3, I'm looking at this line, and row 1, I'm looking at that line. The intersection is the one that you know, so enable here and enable there. That means I have got register 13. Let me give another example. What if my address was 10, 1000? No, not that one. Sorry about that. Let me change that. Don't do that one. Let me say my address is 0010. Yeah, 0010. Yes. What do I resolve? Okay. Yeah, register 2, register 2, register 2. Okay, so the first column and 10, 10 gives me row 3, row 2. And row 2 is here. So if I have enable here and enable there, yes, row 2. Let me ask, what is the address that gives me row 10, register 10? What if I want register 10? What address do I give? By the way, these are questions that I bring. Yes, these are, I mean, I won't ask you to draw this, but I can easily ask you to, I can even provide the diagram, although I probably won't, but I can ask you to tell me. So we need to remember that when we have an address, the most significant half of it is used for the columns, and the least significant half of it is used for the rows. Okay, I'm seeing 1010. 1010. That's register 10. That is column 3. No, column 2 and column 2. Yeah, and row 2. So that's 1010. You are right. Yeah. Now, this is a square. So that is why the size of the row select is the same as the size of the column select. It may not be a row, it might be a rectangular. So we could have, for instance, have a memory that is 32 by, okay, not even by 16, but we could say 32 by 4. 32 is 2 to the power 5. So clearly, we are going to have 5 address bits. So you have to decide how this is going to look like. It could, for instance, be, I don't know, it could, for instance, be 8 rows, 4 columns. Okay, this would still give you your 32. But now this one would need, if your address bits are A4, A3, A2, A1, and A0, this one would be for row select, and that would be for column select. Yeah, thank you guys. All of you seem to be getting it. Okay, so I was just saying that you need to be careful because not all memories are going to be in a square array. However, generally speaking, we call this the register array, that arrangement of registers in some type of geometric array. You have address decoders. Your address decoders, clearly you can see they are the ones that select for you which row, so that you have only one register being uniquely identified on both sides of it. And then you have the output buffers. The output buffers either prevent the information from reaching the data bus, or they allow the information to reach the data bus. So that is a control layer. We are about to finish. We want to finish. Wait, we are going to finish at midday. You have they are saying describe the internal architecture of a ROM that stores 4K bytes and uses a square register array. So this one they've told you it's a square register array. It's 4K bytes, so it's 4K by 8. But really we are interested in that. That one is the size of the register. 4K is 4096, which is 2 to the power 12. And 2 to the power 12 is really 2 to the power 6 times 2 to the power 6, isn't it? Yeah, it's 2 to the power 6 times 2 to the power 6. So it's a square array. It means we need 12 address lines or addresses, 6 for row select and 6 for column select. And our decoders will be one of 64 decoders. And so that means we are going to have 64 rows and 64 columns. As simple as that. Okay. If you have a question about this, how do you know that the word length is 8? They said bytes. A byte, 4K bytes. A byte is 8. The length of a byte is 8. Now, finally, as we end this lecture, let us look at ROM timing. ROM timing, you know, once again, with ROM, we are only reading. So the timing is on the read. Now we are looking at a time T0 when we have some type of address. At a certain time, just hang on a bit. My computer is hanging. Yeah, okay. At a certain time here, which I can call TX, maybe the addresses begin to change to the new address. Maybe the CPU has supplied a new address and it is beginning to change to attain the right levels. And at this point, time T1, we can say that the new address is valid. By valid, it means that those address bits have settled in their position, their new levels, okay? Because you know that it doesn't just happen in an instant, there's some delay. Now, when that happens, we know the next step. We are reading, so we don't need to supply any information. The next step is really to give the command. And because here we are not, this is ROM, we don't really need read write. That one we have already said it's not there. So it's really the chip select which opens up outputs. It really opens up the output buffers. So we give the chip select. You can see the chip select was in the disable state, and now after the addresses have stabilized, it comes into the enable state, it goes 0. Now during this whole time, this dashed line is the high Z, but when the chip select goes low, there is a certain time duration when before the memory actually responds to the chip select. But once it responds, this information that is in the provided address will come to the output. So you can see data outputs valid. At that time T3, data outputs valid, and what happens is that this information gets on the bus and goes to the CPU. And then maybe after some point a new address is provided, and then the whole process starts again. Now the time between when the new address is provided and when the information appears at the output is what we call the access time. I think we said that at the beginning of the lecture. The access time is the time between when the new address is provided and the time it takes and when the information appears at the output. Okay. Now, the time between when the chip select goes in its active low output or active state, which is in this case low, to the time that the information becomes available at the output is called the time output enable time, TOA. It is called time of output enable. So that is the time it takes between giving the enable, the chip select command, and actually information, the thing, the output's responding to that command. Output enable time. We are going to see later on, as we deal with memory later on in other lectures, that we will continue to use these ROM timing diagrams, and I actually bring them. I like them a lot because they really tell you that this person understands the procedure. And I ask them a lot, so really take them seriously. We are going to see more complicated timing diagrams where there are more commands, but here it's just the address, the chip select, and then the output. The delay is normal. It's just that there is a time, if you give the chip select, that signaling has to be transferred to the output to cause a change. All of these things take some time. Output enable time. Once again, the time it takes between you giving the chip select command, because the chip select command is the one that enables the output buffers. You remember when we were looking at it here, this chip select, it was high, but now it goes low. It goes low from the point it reaches its midway. Okay, I think we remember this from first year. And so when you give this chip select, there's a time that that passes between this command appearing at this input and whatever its effect happening at the output. That small, it is a nanosecond. It is not 5 seconds or anything. It's like a few nanoseconds, but that is called the output enable time. It is not the most important time delay here. The most important time delay we are looking at really is the access time. Somebody wanted me to rebound this. I don't know how to rebound this, but since you have asked, let me just redo it again for you. And maybe while we are at it, I can give another example as well. So we have seen, they've told us that this is a square register array. So we know that, and this is 4K bytes, 4K by 8. We are interested in addressing only the words, the number of words, not the byte, not the size, but the words themselves, because they are equal to the number of registers. So 4K, if they say it's a square array, we know that it must be 2 to the power something. Okay, 4096, because 4K is 4 times 1024 is equal to 2 to the power x, and it turns out that actually x is 12. Now, because it's a square, it means the number of rows is equivalent to the number of columns. So it means half of these will be 6 will go for columns, column select, and 6 will go for row select. And so how do we know if we have 6 addresses for columns? It is really 2 to the power 6, which is 64, and that will also be 2 to the power 6, which is 64. So that means for my decoder, I input 6 addresses, A0 to, or A5 to A0, and I will take out 64 rows, for instance. Now we know that, and then for the columns, okay, so this is my row select decoder. the column decoder will be the same. So that means my decoders, for the row decoder, it will be called 1 of 64. And for the column decoder, it will also be 1 of 64. And we know that 4096 is 64 by 64. So if you take the square root of 4096, you will get 64. That's how you know that it is a square of 64 by 64. Now, what if we had this? What if it was, instead of 4, it was 8K bytes memory? It would no longer be a square register array, but it would be 8 times, the best way to do this would be 2 times 4K, so that you have some kind, some kind of square root that you're looking at. But anyway, this, instead of having, if this 4K was 2 to power 12, we know 8K is equal to 2 to power 13. So you first want to get that power in terms of 2. And so here we are going to have 13 addresses if we have 8K bytes. 13 addresses from A13, A12, all the way to A7, A6, A5, all the way to A0. Now, I could say that A6 to, is it A13? No, it's A12. We start at A12, A11, up to A0. This will give us 13, or from 0 to 12 is 13 addresses. Sorry about that. And so from A6 to A0, these are 7 address bits I can use for my row select. And then from A12 to A7, these are going to be 6 address bits. I can use these for my my column, select. Now the column decoders, for the row, it will be 1 of 128 decoder, and for the columns, it will be 1 of 64 decoders. You can already see that actually, because I have 128 rows, I'm going to have 64 columns. This should be equivalent to 8K, 8192 maybe, no, 8096, yes. If you multiply this, should give you 8096, which is equal to 8K. And so you can see already that this is not a square, this is a little rectangle actually. You're going to have 128 rows of 64 registers each. Okay, I hope that that is very clear. Because I would like to stop the lecture, it is time. I want to say before we go that last week, was it last week when I gave a quiz on Zoom, people were very bitter. And I think Uma told me that people were bitter. He didn't really say that people abused me, but he said that people were very bitter with me. So I want to apologize. I didn't know that you have a very difficult time doing Zoom polls, but I think for me, it's really the easiest way to do quizzes. Unfortunately, now I would tell you go to Mwele, and then you start telling me you can't get network and so on and so forth. So it is a bit of a problem for me to grade this course. But I'm thinking of a way to still give you quizzes. However, I am going to say that since you are very bitter, I'm still going to take the other quiz that we did last week. but I think moving forward, we'll find a way that is a bit more acceptable to most people. Catherine, is the test going to be physical or online? Because our physical stay at campus is ending this week. I cannot give an online test. So, and I know you guys, most of you are going to, is anybody going home? I doubt you are going to stay in Chikone and Wandegea. So I'll have to ask, otherwise giving a test that is online in digital communications is almost like a waste of my time. I know that all of you are not going to go. So we'll see with time. I would want to give it at the beginning of May. The problem is that I'm a little busy. But what do we say? Yeah, so everyone is available on Monday because I think the Wednesday class people have to attend another lecture. Can we do 3rd of May? 3rd May. Those who are leaving for home, can we do we have to do a physical test. I'm not going to give you an online test. I can't waste my time. No one is going home. Yeah. Unless we do I'm looking at Monday next week. So Monday next week is, so that people haven't left, Monday next week is 26th, or 3rd or 10th. Either way, I'm okay. But I have to give another second test also. So let's do 3rd May or 26th. I want Maureen to reply to me in the next 2 hours on WhatsApp and give me a date, whether it's 10th or 3rd or next Monday, 26th of April. So I'll leave this to you. Thank you very much. Have a nice rest of the week.